Welcome to solverfy.
So here, we need to note that in order to have an induced EMF, we need for the magnetic field to be perpendicular to the coil or the current, and the change in the magnetic field with respect to time must not equal zero. So the magnetic field must be changing in order to have an induced EMF. So we can say for part A, we know that in vector notation, the magnetic field will be equal to 4.00 times 10 to the negative second Teslas per meter times y k hat. So k hat would be the direction. We know that here the change in the change of the magnitude of the magnetic field with respect to time would be equal to zero. Therefore, the EMF is equaling zero. For part B, it wants the direction of the EMF in part A, but of course there isn't any EMF in part A. Therefore, we have no direction because, of course, the EMF doesn't exist. For part C, however, the magnitude of the magnetic field, or the magnetic field in vector notation, would be 6.00 times 10 to the negative second t over s times t, again, k hat. So essentially, the EMF would be equal to the negative change in the magnetic flux with respect to time. This would be equal to negative A times the change in the magnetic flux with respect to time, dB over dt, and we can then solve. So the EMF would be equal to negative 0.400 meters multiplied by 0.250 meters multiplied by 0.0600 Teslas per second, and we have an EMF of negative 6.00 millivolts. So this would be our answer for the EMF in part C. Now for part D, they want the direction of the EMF, so E would be clockwise. For part E, we have a magnetic field in vector notation equaling 8.00 times 10 to the negative second. Here it would be Teslas per meter per second times y times t k hat. The magnetic flux in this case would be equal to 0.400 multiplied by 0.250, rather, my apologies, 0.400 multiplied by 0.0800 t multiplied by the integral of y dy. And so this is going to equal 1.00 times 10 to the negative third multiplied by t. We can then say that the EMF would be equal to negative the change in the magnetic flux, again with respect to time, and this would simply be equal to negative 1.00 millivolts. We can say that the absolute value of the EMF would, of course, be positive 1.00 millivolts. And the direction here for the EMF would be clockwise, or again, CW. We can say for part G now, because the magnetic flux here is going to equal zero, this means that the EMF is equaling zero, and H, of course, would be none, so there's no direction. We can say for I, again, the magnetic flux is going to be equal to zero, which means the EMF would be zero, and again, for part J, because there is no EMF, there is no direction. That is the end of the solution. Thank you for watching.